Hi folks. The next thing that has to do with solutions that we're going to talk about are colligative properties. And colligative properties are properties that depend on the concentration of solute particles, not what those particles are. So basically how many individual bits you have floating around in a solution, not what those particles are or how big they are, or anything else to do with those particles except that they are there. In particular, two colligative properties we're going to focus on are freezing point changes and boiling point changes. We'll talk about freezing point first. Freezing point depression is based off of the idea that the freezing point of a solution is lower than the freezing point of the pure solvent. You may be familiar with this when it comes to putting salt on the roads. We put salt on the roads, road salt, calcium chloride, to lower the freezing point of water so that we don't have ice on the roads, we just have puddles on the roads, even if it's below freezing. So depression means to make something lower, and freezing point depression, the freezing point of the solution is lower. Why does this happen? If you have totally pure water, the particles can interact with each other, dipole-dipole interactions and hydrogen bonding. They can interact with each other without any obstructions, without anything in the way. But then when you have these solute particles in the water, they get in the way of hydrogen bonding. They get in the way of these intermolecular forces holding these water molecules together. And so when the water molecules try to form a nice orderly structure to form ice, it's actually harder for them to do. It takes extra energy to kind of bump those molecules out of the way, or the ions out of the way, whatever's dissolved in the solution. So these impurities disturb those stabilizing forces between solvent molecules. On the other end of the spectrum, when we're talking about boiling point, solutes do the opposite to boiling points. They raise the boiling points. So if you add salt to water before boiling the water to make spaghetti or something like that, then you are actually slightly increasing the boiling temperature of water. The reason this happens, we have to talk about why boiling happens at all in order to understand this. So boiling has to do with vapor pressure compared to atmospheric pressure. All the time we have air around us pushing down on us, and that's the atmospheric pressure. But you can think of liquid water as having a pressure as well, a vapor pressure, and that's kind of how much these particles want to exit and leave solution. The vapor pressure of pure water is higher than the vapor pressure of contaminated water or water with solute in it. Because basically, if you think of the whole surface of the water here is 100% water molecules, and in this example, it's maybe more like, as it's drawn, it looks more like 50% water molecules. So water just has less opportunity to escape as a gas in this picture than it does here. You have a lower vapor pressure, therefore it takes more energy to make this solution boil than it does pure water. You have to raise it to a higher temperature to make it boil than pure water. As I've already said, there is a common everyday application for this, putting salt on icy roads, is one way that we use colligative properties in an everyday kind of situation to lower the freezing point depression by putting salt on the roads. Antifreeze in cars. Antifreeze doesn't just keep keep the antifreeze from freezing on cold days, but it also helps. It also raises the boiling point so that your engine doesn't overheat. And also, if you've ever made homemade ice cream in an old school way without kind of using the fancy ice cream machines, you add rock salt to the ice to kind of make the ice, the kind of ice water here surrounding your cream mixture even colder. There are 3 factors that determine how much a solution, a solute, can change the boiling point or the freezing point of a solvent. So this is delta T. Remember, delta means change. So I'm talking about how big of a temperature change do we get? It depends on 3 things. The first thing is a constant, and the constant is based off of what solvent you're using. So water has a particular constant versus ethanol versus isopropanol, hexanes, any different liquid you might choose to use as your solvent. M is molality, as we've seen before when we were calculating concentrations of solution. It's one way of calculating concentration of a solute in solution. And this I value here is called a Van't Hoff factor, and it is a measure of the number of particles produced in solution from one molecule or one formula unit of the solute. And I'll show you what I mean by that here. But basically, these 2 values together, molality and the Van't Hoff factor, work together to tell you how many total particles there are in the solution. So molality tells you the concentration in terms of moles, and then the Van't Hoff factor tells you when you have a mole of a substance, how many separate particles is it splitting into. Before we go into too much detail about the Van't Hoff factor, you need to know that there are 2 kinds of solute. You can either have a non-electrolyte, which would be a covalent particle. Those sorts of solutes stay intact. They just stay as one particle when you dissolve them in water. And an example of that would be sugar. Sugar, when you dissolve it in water, stays as a single molecule. It doesn't break up into ions. It's just a single molecule. It's a covalent substance. The other type of solute are electrolytes. These are typically ionic compounds. They dissociate or break up into their separate ions when they are dissolved. So you have at least 2 particles, a positive ion and a negative ion, per one formula. And if it's one of those formulas where you have like MgCl2 where there are 2 chlorines, then you could have even 3 or 4 or 5 or 6. You could have several ions that your substance is breaking into when it's dissolved in water. Electrolytes contribute more particles to a solution than non-electrolytes. At least if you're comparing the same molality, electrolytes create more particles in a solution than non-electrolytes do. Therefore, electrolytes generally have more of an effect on boiling point and freezing point. So long as they have the same molality, they'll have a bigger effect on boiling point and freezing point than non-electrolytes will. So let's look at a few ionic compounds as an example. Sodium chloride. The formula for sodium chloride is NaCl. So when you take NaCl and you dissolve it in water, it splits into its ions, sodium ions and chloride ions. Because there's just one sodium and just one chlorine, for every one molecule or one formula unit of sodium chloride, you just get one sodium ion and one chloride ion. So sodium chloride breaks up into two particles. Magnesium chloride, on the other hand, its formula is MgCl2. When it dissolves in water, it splits into three particles, one magnesium and two chloride ions, because there are two chloride ions here. So magnesium chloride creates three particles in solution. If you have a compound like aluminum sulfate, its formula is Al2 parentheses SO4 close parentheses 3. What do we have here? We have two aluminum ions when we dissolve this in water, and three sulfate ions. So that's a total of 5 particles that aluminum sulfate creates when it's dissolved in water. So if I had a 1 mole solution of each of these substances, I can tell just by looking at the formulas that aluminum sulfate will have the biggest effect on freezing point and boiling point. It will make the freezing point lowest and the boiling point highest. And sodium chloride will have the least effect of these three on melting points and boiling points. It will have the highest freezing point and the lowest boiling point. So let's practice some examples of these. Which of the following solutions would have the lowest freezing point? 0.1 mole solution of glucose, sodium chloride, or magnesium chloride? These are all 0.1 mole, so we don't have to think about anything else other than how many particles each solute splits into when it's dissolved in water. Glucose, C6H12O6. By looking at this, I see that these are all nonmetals. This is a covalent substance, and so it does not split into multiple particles in solution. It stays as just one particle. When I have sodium chloride, that's NaCl, and that splits into sodium ions and chloride ions, so that's 2 particles. And magnesium chloride is MgCl2. Those are magnesium ions and chloride ion and another chloride ion, so that's 3 particles. So when I want to know who has the lowest freezing point, this is all about freezing point depression. The more particles the solute creates, the lower the freezing point will be. So this will have the lowest freezing point. This one will have the highest freezing point, and the sodium chloride will have a middle freezing point. Let's look at another example. Which would, typo, that's fine. Which of the following solutions would have the lowest boiling point? A 0.2 mole solution of calcium chloride, or of sucrose, or of sodium hydroxide? And then which would have the highest boiling point? Okay. All of my solutions have the same molality, so I don't have to worry about that. I just need to think about how many particles each one forms in solution. So I have calcium chloride, sucrose, and sodium hydroxide. Calcium chloride splits into calcium ions and chloride ions and chloride ions. Sucrose is a covalent molecule, so it just has one particle. And sodium hydroxide splits into sodium ions and hydroxide ions, so that's just two particles. So 3 particles has the biggest impact on the boiling point. It's going to increase the, elevate the boiling point the most. And so this will have the highest boiling point. The sucrose will have the lowest boiling point, and sodium hydroxide will be in the middle. I hope this helps.